Yes, Deepak. Yeah.
Okay, thanks. Yeah, so welcome everyone to this talk. It's a pleasure to have Mahesh Viswanathan with us. Mahesh is a professor at UIUC, University of Illinois at Urbana-Champaign. And Mahesh did his BTech from IT Kanpur and went on to his PhD from UPenn, and then he joined UIUC, where he's been since then. And so Mahesh works essentially in the area of algorithmic verification or kind of automated verification, and he uses mainly automata logic and algorithmic techniques based on these. And he works in a variety of areas across across verification and from concurrency to stochastic and hybrid systems, and including some security related topics, which in fact he'll be talking about today. So he'll be telling us about how to use automata to check things like differential privacy notions. So over to you, Mahesh. Welcome.
Thank you so much, Deepak. I'll start sharing my screen. It's sort of great to be here. Thank you for inviting me, Deepak. And it's great to see so many people, familiar names in the audience. I really appreciate all of you showing up. I realize I have a stiff competition, given that there is a T20 game starting around the same time as right now. So I really appreciate all of you taking the time to be here and listening to this talk. So I'm going to talk about basically verifying differential privacy for certain types of programs. This is sort of joint work with Rohit Chadha, who's at the University of Missouri, and Prasad Sisla, who's at the University of Illinois at the Chicago campus of the university. So most of my talk is going to be based on a paper that the three of us wrote that appeared in LICS last year, in LICS 21. And I'll sort of briefly talk about some extensions that we have to those results, and as well as some directions that we are exploring. So let's get started. So the problem is sort of a classical problem. You have a data analyst who wants to basically access information that is stored in a database, and the database contains personal information of individuals. And so therefore you want to, basically allow this information to be shared in a way that is secure. And the problem is that, the responses to queries may reveal private information about individuals that's stored in this database. Now, there is sort of a trivial way to ensure that privacy of individuals is ensured, and that is by essentially not allowing any accesses to this database. So you don't share any information about what is stored in the database. And that seems like a very unsatisfactory solution. But unfortunately, one can show theoretically that is essentially the best one can do if we want perfect security. So there is a classical result by Dinur and Nissim, which shows that if you allow answers to a few random aggregate queries to the database, then the database can be reconstructed, and therefore private information can be revealed. So differential privacy framework was introduced to essentially try to address this issue. So the idea in differential privacy is that instead of having the data analyst access information from the database directly, you sort of mediate the interaction through a through an algorithm called the differential privacy mechanism. So the idea is that whenever the data analyst wants to ask a question about the database, the question is directed to the differential privacy mechanism, which then accesses the information from the database, and then the mechanism responds with an answer to the data analyst. And the key idea in this sort of whole setup is that the way the algorithm responds is by adding noise to any answer to a question that is asked. So essentially, if the accurate answer is some Q of D, then the response of the algorithm is going to be some noisy version of this answer. And so the idea in differential privacy is that to get privacy, you sort of sacrifice accuracy of the answers that you're providing. And the key tension in this is always to sort of ensure privacy while still providing useful or somewhat accurate answers. To get sort of a flavor of what these algorithms might look like, let's look at an example. This is sort of a classical example from social sciences, sort of much before all of this work in differential privacy. So imagine a situation where the government wants to find out how many people in a certain geographical region smoke, and maybe that is to sort of inform public policy in terms of how to invest in infrastructure. And so the problem is individuals may be sensitive about revealing whether they smoke or not, because it could have social consequences as well as potentially financial obligations that may be incurred because of response to this question. So the idea is to do the following. So you advise every individual about to whom you're going to ask this question, whether they smoke or not, to answer that question in the following manner. So they're advised to toss a fair coin. And if the coin results in tails, then the individual is going to answer the question truthfully, whether they smoke or not. And if basically instead the coin results in heads, then they respond to this question randomly. So they toss another coin, and based on the result of the second coin toss, either answer yes or no. Now, the point about this is that essentially, if let's say you notice that I responded yes to the question of whether I smoke, there is no way you can be sure that I'm indeed a smoker. I have a way to sort of claim that my response was not a truthful response because I followed this protocol. So the response of each individual is noisy, but at the same time, the responses can still be used to accurately determine the fraction of people who smoke in a certain geographical region. So essentially, every smoker, according to this protocol, has a 3/4 probability of answering yes, whereas every non-smoker has a probability of 1/4 of answering yes. And if you do the calculation, essentially the expected number of yes responses has a close correlation to the accurate number, to the actual fraction of people who smoke in that population. So by estimating the number of yes responses, you can sort of gauge exactly how many people smoke in that region. So let's look at the definition of differential privacy a little bit more carefully. And in some ways, I'm going to sort of specialize the definition to the context that I'm going to look at in this talk. So once again, just as a setup, so we're really analyzing some property about this differential privacy mechanism, which is this block M that I'm showing in this cartoon here. And if you look at that algorithm, the algorithm gets a stream of responses from the database, basically a stream of answers to queries, and it produces a stream of responses in reaction to those answers. And the key idea in differential privacy is to ensure the privacy of every individual. And the way that is ensured is by demanding that the differential privacy algorithm's answers are similar, whether the algorithm is interacting with a database D or whether it's interacting with a database with the information of one more individual. So you ensure the privacy of an individual X if essentially the answers that the differential privacy mechanism provides to the data analyst is similar, whether the database contains the personal information of X or not. Now, the key idea is to basically quantify what it means for these responses to be similar. So one thing to notice, and will sort of become clear as we look at some examples, is that typically these differential privacy algorithms are sort of parametric in some parameter epsilon, which sort of denotes the privacy budget that is allocated. So depending on how much privacy budget you allocate to the algorithm, its sort of basically responses will change potentially. So the input to this algorithm is a sequence of numbers or answers to aggregate queries. And so if I think about essentially the fact that I want the response of the differential privacy algorithm to be similar based on two databases, one which contains the information of an individual and one which doesn't contain the information of the individual, and let's say the inputs to this algorithm itself are aggregate queries, then I can think about essentially the inputs on which my algorithm is obligated to respond similarly to be those where, let's say, the numbers that I'm getting as input are close. And sort of one standard way to sort of talk about closeness is to say, I consider two inputs to be close if, let's say, the number at each position in the input stream is within distance 1 of the other one. Okay, and of course, this 1 is just an arbitrary number. You can tweak it to whatever you want. And of course, you can look at other notions of what inputs are considered close. So you have some notion of adjacency, which characterizes inputs that are close. And this is the particular notion that I'm going to use in this talk. And then having this notion of close inputs, one can talk about the obligations of the differential privacy algorithm. So we'll say that this algorithm M is d epsilon differentially private if it is the case that for any pair of adjacent inputs, the probability with which the algorithm outputs a certain value on the first input is close to the probability with which the algorithm outputs a certain value on the second input. And closeness is characterized by the fact that these probabilities need to be related by basically a factor of e to the d epsilon. So this is sort of a particular notion of epsilon of differential privacy. Sort of there is a slightly more general notion of epsilon differential privacy, where you not only have a multiplicative factor that characterizes the closeness of the probabilities, but you also have an additive factor. So these are called epsilon delta differential privacy. But in this talk, I'm just going to talk about this notion of differential privacy. So I don't want to introduce that second notion as well. Any questions at this point?
Yes, Mahesh, sorry, I missed, what is small d?
Small d is just this parameter that characterizes the property. So I'll say it is d epsilon differentially private if this relationship holds. So d is just a number you can imagine that is given. So some algorithms will be, I don't know, just epsilon differentially private. In other words, d is 1, or sometimes there'll be 2 epsilon differentially private, in which case d is 2, and so on and so forth.
I see. Okay, fine. Thanks.
Any other questions before I move on? Okay, so let's just look at an example again, and sort of this is a little bit more concrete with a program to sort of give you a flavor of how these things look. So this is sort of a classical technique called the sparse vector technique. So here, basically, the algorithm gets a sequence of answers to queries, and I'm sort of just denoting it as this sequence Q1 through Qn, and it has a threshold as well. And the goal in this algorithm is to output the first value in your input stream that is larger than the threshold. So that's sort of the goal of the problem. But of course, sort of the differential privacy algorithm is going to sort of give some approximate answer to this question. So, so essentially the way the algorithm works is what it does is it first perturbs the threshold. It sort of basically samples from a particular distribution called the Laplace distribution with certain parameters. So, this Laplace distribution is a distribution that looks like this. It's sort of very similar to, let's say, the Gaussian or the normal distribution with some differences. Basically, the important thing I want you to notice is that basically it's a distribution where the parameters to the distribution determine the mean of the distribution. So the second argument to the Laplace distribution determines the mean of the distribution. And the first argument, which is called the scaling parameter, basically determines the spread of the distribution. So the lower the first parameter is, the more spread out the distribution is, the higher that value is, the more concentrated the distribution is around the mean. Now, another thing to basically notice about this distribution is that suppose I sample from this distribution and with a certain mean, and I, let's say, add a constant. So that gives you a random variable that is basically sample from this distribution plus this constant. That is the same thing as, sampling from the distribution where the mean is translated by the constant, because just adding the constant is basically shifting the curve by some fixed number. And sort of these two views are going to be convenient to keep in mind in this talk. So in other words, the first line of this code says, basically sample from the Laplace distribution with a certain scaling parameter where the mean is the threshold. So in other words, the distribution is centered around the threshold. I could have instead thought of basically sampling from the mean, which is 0, and then adding the threshold after sampling with the mean equal to 0. Okay, so this algorithm is basically going to first perturb the threshold that is given as input, and then it's going to do the following. In a series of steps, it's going to read each query one by one. And then when it reads the query, it's again going to perturb the query. It's going to perturb it by, again, sampling from the Laplace distribution with the mean, which is the query value. And then it's going to compare the noisy query with the noisy threshold. And if it turns out that the noisy query is larger than the noisy threshold, it will say that this is the index at which you first find a query which is larger than the threshold, and it will stop. Otherwise, it will continue processing the queries. So in other words, so the goal was to output the first index where the query is larger than the threshold. This algorithm will output that index in unary. It's encoding that index in unary. So it's outputting a sequence of bottoms followed by a top, where the first time the query increase is larger than the threshold. But the second thing is also, it's not comparing exactly the query with the threshold. It's basically comparing a noisy version of the query with a noisy version of the threshold in order to make the decision of whether the query is larger than the threshold. And one can prove that this particular algorithm is epsilon differentially private. So you can see that some, these numbers that show up in these parameters play a role in exactly what, how differentially private the algorithm is. In general, ensuring privacy is sort of subtle. So if I, let's say, take this algorithm, which is the one we just saw, and I just sort of, and I just claim that this is differentially private, and I tweak it slightly, I essentially add an additional statement to my algorithm where, after I perturb the threshold, I let the world know what is my threshold that I'm going to use for comparison. It turns out that this algorithm is no longer going to be differentially private, no matter what value of D I choose as a parameter to my property. Okay, so differential privacy is subtle, and there are sort of examples of protocols that people thought were differentially private and are not, and so on. And computationally, unsurprisingly, it's a difficult problem as well. In general, the problem is undecidable, and it's not easy, difficult to show. And it's also easy to show that, even very simple examples of programs you can consider, and the problem becomes undecidable. So the goal, at least, some of the work that Rohit, Prasad, and I've been doing is to basically understand when is this question decidable, and I'm going to sort of share some results in that context here. So
the undecided, I have a question.
Sorry. Yes, go ahead.
So the undecidability result, it applies to straight line programs? Loops?
So, yeah, you can say it applies to straight line programs. Yeah, because the thing is, you can sort of sample from these real values, and then you sort of have these constraints that can show up to be influential in making the decision of whether it's differentially private or not.
So real numbers is the reason for undecidability.
Yeah.
Okay. Thank you.
So, so in this talk, I'm going to sort of introduce this automata model, and essentially we're going to look at this automata model. And the important thing is that this automata model will allow us to talk about whether an algorithm is differentially private, no matter how long the input stream is. So, this is in contrast to some other decision procedures or approaches towards establishing differential privacy, where typically you sort of assume that you look at a finite sequence of input values or something like that. And differential privacy is sort of an intrinsically difficult problem because it's sort of parametric, right? The algorithm itself depends on this parameter epsilon that influences decisions. And the goal in establishing differential privacy is often to show that the privacy claims hold no matter what value of epsilon you choose. And so it's sort of an intrinsically parametric verification problem. And so that's sort of a factor that makes the question difficult. And what we'll sort of do is essentially identify certain necessary and sufficient conditions on the automata, or rather more on the graph that underlies the automaton. And these will be sort of very simple to check. They can be checked in linear time, and it will sort of either prove that the algorithm modeled by the automaton is differentially private, or it will prove that it'll come up with a counterexample that demonstrates that the algorithm is not differentially private. So before sort of presenting the result, I just sort of want to situate this result in this sort of, this setup of verifying differential privacy. It's sort of a very vibrant field. A lot of people are working on it. So broadly, sort of the work can be classified into three sort of broad streams. So one is sort of trying to come up with ways to construct a proof that an algorithm is differentially private. So these are sort of approaches where maybe you come up with a type system that establishes that the algorithm is differentially private, or you sort of come up with a proof in some sort of logic, a whole logic kind of approach towards establishing differential privacy. And so the idea in these approaches is, of course, that there may be algorithms that are differentially private, but let's say your approach cannot establish that they are differentially private. So these are like, if your approach succeeds, then you'll prove that it's differentially private. But if your approach fails, you cannot conclude anything about the algorithm. So these are sort of sufficiency approaches to proving differential privacy. Another sort of stream of work is in sort of the dual problem, trying to discover bugs. So there are approaches to trying to prove or search for counterexamples that show that the algorithm is not differentially private. So these approaches sometimes use statistical approaches to kind of identify these examples that demonstrate that the algorithm is not differentially private. And then there is sort of a line of work that tries to identify when is the problem of differential privacy decidable, And some of this work sort of relies on, looking at this program and then reducing the question of whether it's differentially private to a question about first order theory of reals, including exponentials. And the idea in this approach is typically to sort of construct a formula that lies in a decidable fragment of the first order theory of reals with exponentials. So some of you may know that, one of the long-standing open questions in mathematics and logic is whether the first order theory of reals with exponentials is decidable. But there are some fragments that are known to be decidable. And so this approach tries to basically reduce the question of deciding differential privacy to a question of checking if a certain formula belongs to the theory of reals. And this is sort of a very different kind of a result in that space. It's sort of about using automata theory in some sense, but also, as I mentioned, it is about establishing differential privacy when the stream of inputs could be potentially of unbounded length. So I will sort of share now the automata model. And of course, if there are any questions, feel free to interrupt me in this middle. So let me tell you what this
Mahesh, can I ask a question?
Yes, go ahead.
So yeah, just to understand the definition a little better. So the in that example of the stream that you have, you want to output the position of the type place when it goes out of the threshold. So what is so I guess the query there is what the value of the threshold?
The query is, so the input to the algorithm is basically a stream of numbers, which are queries. And then you also have the threshold. So the input is basically a stream of real numbers, you can imagine. Okay, if I, let's say, fix the threshold to be some fixed number, the input is a stream of real numbers, and the goal is to check, and the goal is to output the first real number, which is larger than the threshold.
Okay, and what is the capital S there? So sorry, what is the notion of closeness of the input here, and what is that capital S?
Yeah, so the capital S is the outputs it can produce. So in this case, the outputs are basically values of indices, right? So here the output is the number is being encoded in unary. So the output is basically a sequence of bottoms followed by a single top. So the number of bottoms indicates the index. And so the output could be, oh, on this particular input, am I going to output 2 or am I going to output 3 and so on? So different numbers turn out to be the possible output. So S could be the number 2, number 3, and so on. And the closeness of inputs is, so remember the input is a sequence of real numbers, and 2 sequences of real numbers will be considered close if at every position, 2 real numbers in the inputs are within distance 1. So they're within 1 of each other. Okay. Okay, so just to give you a flavor first of the automaton, and then I'll show you the automaton. So the automaton is sort of a parametric automaton. As I explained, these differential privacy algorithms, their decisions depend on this privacy budget epsilon. So it's a parametric automaton, and it has only 2 variables. So the first variable is something that is used as a storage. So to remember something about the sequence of numbers it's seen or the sequence of decisions it's made. And so that variable I'm going to denote by X. The other variable is basically a variable that's going to be used to sample a real value. And it's going to be, so every step you're basically going to sample a real value. The sampled real value is going to be stored in this variable that I'm going to call inSample. And you're going to make decisions based on what is the real value that has been sampled. Okay. So in each step, you're going to sample a value from the Laplace distribution. The Laplace distribution has two parameters. The parameters that are used for this distribution are going to be determined based on the current state of the automaton. So the current state is going to tell you what are the parameters that you're using in the distribution. And you sample this value and you store it in this variable in sample. Next, the inputs of the automaton are going to be divided into two classes. There'll be inputs from which there are going to be states from which you're going to read an input value, and there are going to be states where you don't read anything and you just take a step. So if you're in a state where you're reading an input value, what you're going to do is you're going to read a real number, and you're going to add that real number to the value you sampled, and which is stored in sample, okay, in the variable in sample. Then what you're going to do is you're going to compare the value in sample with the value that is stored in the variable X. And based on how they compare, you're going to take a transition. You're going to change your control state. And so the effect of the transition is, of course, to change your control state. And you can also, after you take the transition, decide whether you want to change the value you've stored in your variable X. And the way to change the value stored in the variable X is to just store the new value that you've sampled. Okay, so it's very restricted in the way you can change the value that is stored. You can only store the value that you've sampled, and that's what you do. Okay, so let's look at an example and it'll become a bit more clear. So this is the SVT algorithm that we've been looking at throughout this talk, right? And so I can model it as an automaton. So the automaton looks like this. So as I mentioned, there are two types of states. There are the states where I'm not reading any input value, and that I'm going to denote by these rectangular states in these pictures that I'm drawing in this automaton. So in this case, I'm imagining that the threshold itself is not part of the input. It's fixed for the algorithm, and then in the first step, you're perturbing the threshold, and that step is going to be modeled by the initial state here. So it's a non-input state, and this is to be contrasted with an input state where you read a real value from the input, and then you change the sampled value based on the real number that you've read from the input. And so those I'm denoting by these circle states here. Transitions in the and then I mentioned that you're sampling in each step, and the parameters that you use to sample depend on the state. So the state is decorated by numbers, by two numbers. The first number basically affects the scaling parameter of the Laplace distribution, and the second value affects the mean of the Laplace distribution. So in this case, basically, since the number is half and 0, you're going to sample from the distribution, which is epsilon divided by 2, 0. Okay, so remember, epsilon is still a parameter. These automata are parametric in epsilon. So if I change, so basically you run this automaton for a fixed epsilon, and you can keep changing the automaton and the behavior will change, right? So epsilon is always a parameter here. Then you can look at the transitions. The transitions have three components. There is the guard, which tells you whether to take the step or not. And if you notice, the guard basically compares the value you've sampled with the value that is stored in the variable X. The second component is the output that you produce on taking the transition. The output in general can be a real number or can belong to some finite set. In this case, at each step, we are either outputting bottom or top. So that's the output. And then there is the decision of whether you're going to store the sample value in your variable X or not. So that's a Boolean value. So in this case, it's false, which indicates that you've chosen not to store the value. Okay, so let's just walk through this program and see how it corresponds to the automaton. In the first step, you just perturb the threshold. So what you do is you start from the initial state, you sample according to the distribution that I'm taking the threshold here to be 0. It's a non-input state, so you don't perturb the sample value. You take the transition, there's nothing stored in the variable X. So you take the transition, you output, let's say bottom, in this case, just a dummy value, and then you store that sample value in the input. So the variable X is going to store the noisy threshold throughout the algorithm. Okay. And then in the loop, you're basically reading each real value. So you perturb the input and then you check if the input is larger than the threshold. And if it is larger than the threshold, you output top and you terminate. So in this case, whenever you take this step, you don't change the perturbed threshold, which is the value stored in X. So the third component of these transitions is always false. And then there is the comparison and then the output value. If in the case, if it is the case that the perturbed query is not larger than the perturbed threshold, then you just stay in the same state and continue the algorithm. So that's sort of the correspondence between the algorithm and this automaton. Any questions?
Hello, sir. Sir, I have one question. What is true and false? Can you once again?
Oh, true and false. So it's just there are three components to the transition. The first component is the guard that tells you when the transition can be taken. The second component is the output produced. And the third component tells you whether you're going to store the sampled value in your storage or not. Okay, so when the first component is basically true, it means that you take this transition no matter what the situation is. Otherwise, you sort of compare the sampled value with the value stored. And the third component tells you whether to store the sample value in your input or not.
Okay, so from Q1, the two transitions we are taking, we are not storing any values in X.
We're not changing the value stored in X. Yes.
Okay.
In the two transitions out of Q1, you're not storing you're not changing the value stored in X. The value stored in X is only changed in the transition from Q0 to Q1.
Okay, got it. Yeah.
Okay. So just some, additional terms just to sort of explain what this automaton is, and so that I can define exactly what the problem is and I can state my results. So I'll call a transition an assignment transition if it is one of the transitions where I've chosen to change the value that I stored in my variable X. Okay. Now I'm going to make an assumption just so that all the definitions are okay. So remember, the variable X can be compared, and we want to make sure that whenever you choose to compare the variable X, it actually has a value, so that, things are not weird when I'm looking at an execution of the automaton and I can really define its semantics. So without loss of generality, I'm going to assume that from the initial state, there is only one transition. The transition is taken no matter, its guard is always enabled. And, it's a transition that stores a value in the variable X, so that after that transition, variable X is always defined in my execution. The automaton will make some assumptions. So the automaton is kind of deterministic. So from any state, there is basically exactly one transition that is enabled based on the guards. So the guards are disjoint. And the second thing is, I'm also going to assume that the output uniquely determines which transition I have taken. So, different different transitions from a state have different outputs. So what this means is, if I know the start state of my automaton and I tell you the sequence of outputs, I can tell you exactly what are the sequence of transitions that you took in the automaton. So this is a somewhat strong assumption in the modeling of this automaton. So in general, I'll talk about paths. So a path is just a sequence of transitions, but in order to really define the probability, I also need to know what are the sequence of inputs that are read at each step. So a path is basically transitions along with the inputs that are read at each step. And so for a path, I will talk about the inputs that are read by in sequence of row and the outputs that are produced by out sequence of row. Okay, and the probability of a path starting from the initial state is completely determined by the value that I assign to the privacy budget. right? So, so basically, I will talk about the probability of a path given a privacy budget. I'm not going to define this probability precisely. It'll just get a little bit technical because I need to talk about the distribution and things like this. But you can imagine that you can define this probability in a precise manner. So, so there are two computational questions you can look at. So one is the d epsilon differential privacy question. So given an automaton, you want to find out, and given an automaton and a number d, you want to find out if for all values of epsilon and for all paths, for all pairs of paths, such that the two paths have the same output and the two paths have input sequences that are adjacent, the probability of those two paths is close, according to the obligations of d epsilon differential privacy. The question that we are going to look at in this talk and in this paper is actually a slight variant of this question, which I'll call differential privacy. So the automaton is differentially private if you can find some value for d such that the automaton is d epsilon differentially private. Okay, so and essentially the result is going to be that there is a linear time algorithm to solve the second problem, and the linear time algorithm will actually also output a value for d such that the automaton is d epsilon differentially private for that number, if it is the case that it passes the test. Any questions?
Could you please repeat what is out sequence and in sequence?
Yeah, so given a computational path in the automaton, essentially what is important is the sequence of inputs that are read along that path and the sequence of outputs that are produced. So out sequence is the sequence of outputs that is produced, and in sequence is the sequence of inputs that are read. So the sequence of inputs is the sequence of real numbers, and the sequence of outputs is the sequence of outputs produced. Yeah. So in differential privacy, you want to make sure that if you get close inputs, then the outputs, then the probability of producing the same output is very close. And so that's sort of the reason why you're looking at those two things.
Sir, I have one doubt. What is meant by adjacent input sequences?
Yeah, so adjacent input sequences is, in this talk, it means that, we're looking at a sequence of real numbers as inputs. So we'll say that two sequences of real numbers are adjacent if in every position, the two input sequences have real numbers that are at most one apart.
Okay, okay, got it.
Yeah, so for now, I'm going to assume that the output alphabet is finite. So I guess I have like 10 minutes. So what I'm going to do is essentially give you a flavor of what our necessary and sufficient condition is, and not share the intuition about why the proof works. So there is this notion called a leaking cycle that plays an important role. So a cycle in this automaton is just a path that starts and ends in the same control sequence. And we will call a cycle leaking if it is the case that you look at the transitions in the cycle, one of the transitions actually assigns a value to the storage variable X, and another transition, possibly the same one as the assignment transition, compares the value that is stored in the variable X to the value that is sampled at that step. Okay, so let's look at an example. So here is an automaton that describes a slight variant of the example that we've been looking at. So this automaton tries to do the following. It reads a sequence of real numbers, and it wants to check that the sequence of real numbers is in descending order, and it outputs the index of the first position where the input sequence is no longer sorted in descending order. So basically, it checks that the sequence of inputs is in descending order, and as soon as it finds the first position where that ordering condition is violated, it outputs the index of that position. So the way to do this potentially in a differentially private manner is you read the input sequences, sorry, you read an input number, perturb it, remember it, read the next input number, perturb it, compare the perturbed input numbers. If they're in the right order, continue. If they're in the wrong order, output top. Okay, and this automaton has a leaking loop or a leaking cycle. So if you look at the self loop on the control state Q1, it's a cycle. It has a transition whose guard compares the value stored with the sampled value. And it also has a transition, namely the same transition, where actually you store the value in the variable X. Okay, so if you look at the third component of that transition, it is set to true. So this is a leaking cycle. Another condition that is going to be important is a leaking pair. So it's a pair of cycles, C1 and C2, that are connected by a path called rho. Let's call that path rho. So we're going to assume that neither one of these cycles is a leaking cycle. So the way we're going to assume that neither one of these is a leaking cycle is by saying that neither one of these changes the value that is stored in the variable X. Okay, and we're going to assume that somehow that there is a transition in one cycle that compares the value X with the sampled value in a different order than another transition in the second cycle compares. So let's assume, for example, that there's a transition in C1 that checks that the sampled value is less than the stored value. And in C2, it checks that the sampled value is greater than equal to the stored value. And the last condition that is required for a leaking pair is that basically the path connecting these two cycles ensures that the value stored in X only increases. Okay, so remember in C1 and C2, the value of X doesn't change. So there is a value stored in X at the start of C1, and there is a value stored in X at the start of C2. We want to make sure that the value stored in X at the start of C1 is at most the value stored in X at the start of C2. Okay, so it's just a technical condition. So let's just look at an example. So this is again a variant of this SVT algorithm. So in the SVT algorithm, I was outputting the first index where that is greater than the threshold. Now here, I'm sort of looking at a slightly more complicated thing where I'm going to output first, I'm going to look at the sequence of inputs. I'm going to first check that they're all less than the threshold. Then I will check that they're all greater than the threshold. And then the first index, when again the input becomes less than the threshold, I'm going to output, I'm going to stop and output the index of that position. So now this has a leaking pair because if you look at the self loop on the state Q1 and the self loop on the state Q2, they satisfy the conditions of a leaking pair. Basically, the value of X is not stored in the path that connects the two cycles, and the two cycles compare the sample value with X in different orders. Okay, and so the main result is that, okay, so we'll say that an automaton is well formed if it has no reachable leaking cycle or no reachable leaking pair of cycles. And the main result is that the automaton is differentially private if and only if it's well formed. So I won't have time to talk about why this proof holds. It's sort of somewhat a difficult proof. The proof is long as well. And it's sort of very subtle to get right. But the important thing that maybe is worth highlighting as we are looking at this theorem is that the condition for checking whether it's differentially private involves checking for cycles of a certain type in the graph. So essentially checking whether an automaton is differentially private just involves checking strongly connected components in the graph and checking that those strongly connected components have transitions of a certain type and so on. So it's sort of a very easy check. So I'm going to skip all this stuff. Skip all of this stuff. So just a pointer that the condition that I stated in that theorem applies to automata where the output is from some finite set. In our LIX paper last year, we actually looked at automata, as I mentioned, where the outputs can either be from a finite set or from real values. And essentially, those observations can be modified to account for automata that have real valued outputs as well. The condition becomes a little bit more tricky and the proof becomes more complicated, but it can sort of, it can be handled. So I just want to quickly conclude to give a few minutes for questions. So we looked at this automata model that models certain differential privacy algorithms, and you can basically come up with an efficient algorithm to check whether these automata are representing algorithms that are differentially private, and those conditions rely on checking these underlying graphs. So one of the things that I didn't sort of, we couldn't get into because I didn't get a chance to talk about the proof so much, is that in some sense, there are these parameters that decorate the values that are sampled in from the distribution. Those parameters, sort of the proof of correctness sort of relies in a modular way on those parameters. So in other words, if I establish, let's say, differential privacy of an automaton with certain values decorating the state parameters, then the same proof also allows us to establish a slightly modified differential privacy claim for automata where those parameters are tweaked. So it sort of basically gives you this algorithm that allows you to basically get differential privacy proofs for a variety of parameter values that are set in the automata. Okay, and some of the things that we're looking at is, so we have sort of results that extend these proofs of differential privacy to automata where you have more than one storage variable. So you can have multiple storage variables, and you can use that to in the algorithm. The proofs become slightly more complicated. We can also sort of generalize the conditions that are used in the guards, and that allows us to sort of model a larger class of algorithms. So the definitions of the automata, the definitions of necessary and sufficiency become more complicated, but the complexity of the algorithm remains the same. So it's sort of still a linear time algorithm. So I mentioned that if our algorithm shows that an automaton is differentially private, then it computes the value of D for which it manages to prove differential privacy. So one question to ask is, how tight is that? Or what is the complexity of computing a tight bound on D? So that's, I think, an interesting question. It's sort of related to other questions in the automata space for probabilistic automata and stuff like that. My suspicion is that the problem is going to be undecidable, but whether it can be effectively approximated would be an interesting question. And the other thing I would like to mention is that we looked at this particular version of differential privacy where we are checking if there is a value of D so that the automaton is D differentially private. But you could also ask whether the automaton is D epsilon differentially private. And that turns out to be a computationally very different problem. We don't know how to solve it even for the automata that we have, but it's sort of worth looking at. And lastly, in differential privacy, as I mentioned, you trade accuracy for privacy. So in general, when you come up with an algorithm, you'd like to not only prove that it's private, but you'd like to prove that the values it outputs are still close to being the right values. So you could try to see how to check accuracy of algorithms as well. And that's sort of that's an area of interest that that's sort of being actively pursued. And I'll stop there. And I'm sorry I've sort of exceeded my budget of time, but I'm happy to take any questions if anybody has any.
Yeah, thanks a lot, Mahesh, for that interesting but little heavy talk. But yeah, if anybody has questions, please go ahead.
Yes, I have a question, Mahesh. Yeah, thanks for the very nice talk. So I was wondering, in this definition of differential privacy, you used the exponential e power d, and then that led to undecidable, open questions in the first order theory of real with exponential and so on. Is there a way to like change the exponential to something else and still get some answers out?
Yeah, so for example, there are sort of approaches where what people do is, for example, you take a program, you write down, you basically code what it means for the program to be differentially private as a formula, right? I mean, it's basically you just write it as a formula. That formula, because of the definition of differential privacy, is going to involve exponentials. But then, you may want to prove. So one approach that some people have taken is, you think about that exponential as an uninterpreted function, and then you try to see whether the formula holds in this sort of uninterpreted world for the exponential. So maybe you write down certain axioms that the exponential function needs to satisfy that may be critical, and then you see whether that first order formula is true for the real numbers for any function that satisfies whatever certain properties that you've written down in the formula. So that's sort of a way that people have tried to, establish proofs of differential privacy by approximating the exponential function.
No. My question is there, can you change the definition of differential privacy to get rid of exponential and use some other function and still get some sensible answers?
So your question is how integral is the role of the e to the something, right? So I think the reason why e to the something sort of shows up is that a lot of the algorithms that rely on adding noise rely on distributions where the probability density function is some function of the exponential. So they show up. I mean, at least this is my understanding of why that shows up in the definition.
Okay.
So like this Laplace distribution is one of them. There's sort of an exponential distribution, but also another very popular thing is just to use the normal distribution when you're adding noise. And all of those sort of have this dependency on e to the something. And so this seems like the right way to define a differential privacy for all these algorithms. But so what I was trying to respond to in that context is that sometimes you could sort of establish that this definition of differential privacy also holds by looking at a different definition that the algorithm may satisfy, which is stronger, and that sort of just implies this definition kind of thing. Yeah.
Okay. Thanks, Mahesh. Yeah.
Are there any other questions, Mahesh?
Can I ask one more, please?
Yeah, sure, Sivat.
So in that, I was curious in that SPT program that you have. So how accurate is the answer, like in this queries and then?
Yeah. So for our algorithm outputs. So I guess I didn't get to it. So it basically outputs exactly what has been proved for that algorithm in terms of previous results. So that it proves it's exactly whatever one different. It's a
my question is,
and that's what it.
Even more basic. So like just the algorithm that you showed to say that whether the first index, which is bigger than the threshold, so you perturb both the threshold and the input, and then you output top at some point. So let's say you output top at I. So how far is it from the real answer?
Okay. So you're asking how good is that algorithm? If I was really interested in looking at the thing. So that's sort of an interesting question. So the question is, how do you define the accuracy of differential privacy algorithm? So typically, the way one sort of looks at defining the accuracy is that one cannot prove differential privacy, the accuracy of an algorithm for all inputs. Okay, so for example, if let's say I give you an input where the real numbers are very close to the threshold against which you're comparing, then with the 50% chance each of your comparisons is going to be wrong, and so you're going to get an index which is not at all close to the actual value of the thing. So typically, when one sort of tries to prove that a differential private algorithm is accurate, what one does is one only looks at inputs that are like sort of very robust with respect to the problem that one is looking at. So in this case, you want to basically look at inputs where the real numbers are, let's say, far away from the actual threshold you're comparing. And then you can prove some claims that with high probability that the index that this algorithm outputs is essentially the same as the index that you would output if you didn't do any perturbations.
Yeah. So I had a couple of questions, Mahesh. One was I mean, one of the problems you had in a slide was to show I mean, can you tell whether a given automaton is d epsilon whatever private
Yeah.
for a given d and given epsilon? So isn't that an understandable
So it's not
problem,
for a given d and epsilon, for a given d, but you want to check if it's differentially private for all values of epsilon.
Okay.
Yeah. Yeah.
And so
I
thought you said that
you're asking whether it's an easier question than the other one, right?
Which
so
one?
I don't know if it is easier.
No, so the original one, I thought you said one version was undecidable, right? The original question of whether something a given protocol is
Yeah. So the version, so there are basically, let's say, two versions that I talked about in this talk. So one is, let me go back. So one is where you're given D and you want to find out, is it D epsilon differentially private? And the other is you want to find out, is there a D such that it's D epsilon differentially private?
Right.
Now, both those problems turn out to be undecidable. Most people look at the first question where you're given D and you want to find out, is it D epsilon differentially private? Some of the decidability results that have been established there, I don't know whether they extend to this other problem that I talked about in this talk, where I want to find out, is there a D so that is D epsilon differentially private? Part of the reason is, if you, let's say, look at just coding it in logic, then this adds another quantifier. And then it seems like maybe it's a more complicated question. I don't know. On the other hand, in this particular setting, at least right now, we don't know how to prove D epsilon differential privacy when D is fixed to a particular
So
value.
the undecidability result doesn't carry over to the class of automata that you look at.
Oh, yeah, no, for this class of automata, it's okay. Yeah, I don't know. Yeah, I don't think, at least that proof doesn't go. Yeah, but I don't know if there's another proof. Yeah.
Okay, and my second question is similar to what Srivatsan asked. How good is, I mean, what use is these this automata model of these algorithms? I mean, typically the first time I heard of differential privacy was in the context of, you have a database and you make a query and you get, I mean, you don't want to leak some information from that, whether, like, as you say, whether one of those guys smokes or not, a person in the database. So how does, I mean, does your automaton model help to, formulate differentially private, answering mechanisms there for those kind of problems, or is it? I mean, I'm asking how does it apply to the kind of original problem that you motivated?
So is your question, does it help come up with algorithms, or is that your question? So I don't know if it helps come up with questions, algorithms. So I think we've been sort of mainly looking at the verification question. One could potentially look at, let's say, the synthesis question, maybe. I don't know exactly what it means in this context, which is you sort of have an automaton or a template of an automaton, and then you want to search for an automaton that satisfies some privacy requirement and potentially some requirement on the outputs in some fashion. So it definitely doesn't answer the question about how to do algorithm design. It just may help answer the question of whether it's differentially private, if an algorithm is differentially private, if it can be modeled in this framework. Not every algorithm can be modeled in this framework.
Yeah. So I had one question.
Yeah, go ahead, Prashant.
So with respect to the first version, you said, is there, where you talked about, is there a D such that the algorithm is D epsilon differentially private? Is there a limit on D that you are interested in? Because if D is arbitrarily large, then this question is trivial, right?
So this question is trivial for arbitrarily large D. So first, we don't have a bound on D. But what I don't immediately see is why the question is trivial.
So because if D, so let's say e to the D epsilon is 1, then it is trivially true, right? The probability will always be less than e to the D epsilon times. Sorry.
Well, so maybe I got these numbers wrong. So you definitely want that the coefficient to be less than 1. So maybe I didn't put a minus maybe when I was supposed to put, or so you can think of D as basically, yeah. So no, I'm sort of getting confused. So basically what you want to prove, right? What you want to prove is I fix the value of D, and I want to prove that the algorithm is D epsilon differentially private for all values of epsilon. So no matter what large number of D you give me, I need to prove that it's also differentially private when epsilon is really, really, really small.
Okay. Okay.
Yeah.
Okay. Yeah, that makes sense. Thanks.
Sure.
Are there any more questions? Okay, so in that case, let's give Mahesh a hand. Mahesh, thanks a lot for a great talk.
Thank you very much.